right? Well, the significance of this is when we talked about this, it's just one bounce, right? And we said it was just one bounce, but if you keep making waves and it keeps bouncing, the amplitudes will keep adding up, right? Because you keep getting energy, you keep putting energy into it. If it doesn't escape anywhere, it just adds up. So in this case, it looks like this because it's one wave that bounces, comes back, and then it leaves, right? So if you have a wave that is confined the way a guitar string is confined, as long as you keep giving it energy, the energy should keep accumulating. But the reason we don't see this actually happening is because you pluck it once and you leave it as it is, right? The energy doesn't leave. It just keeps bouncing around there. And this is what we call resonance. The other example, if you try to, something that actually keeps collecting energy is sound and something that vibrates, right? And you might have seen this before, the cup and the woman singing, and when she sings, she breaks the cup, right? The way she does it is her voice keeps giving this energy. The energy keeps bouncing in the cup as vibrations, and it keeps accumulating, right? Of course, some of it does leave because it's vibrating, it makes the air vibrate. But if she gives it more energy than it can give off, it keeps accumulating to the point where it breaks. This is the concept of resonance. Every time if you keep doing it, the amplitude keeps increasing unless some of the waves are allowed to escape. One thing that is interesting though is because if you bounce it inside without loss of energy, you only have to do it once, right? And the sending wave will go on forever, theoretically, if no energy comes out of it. And they use this in instruments, right? The reason we use violins with big bodies, right, and guitars with big bodies is so that the sound can bounce around inside it and resonate and become bigger amplitude and sound bigger, louder, right? So this is the frequency of a guitar, right? At certain frequencies, there's bigger amplitudes, right? Because at these frequencies, they fit exactly the length of the string, and so they can accumulate energy, right? So the fundamental frequency is 100, right? And then the next harmonic is 200, 300, 400 is multiples. All these waves have wavelengths that have the same, that fit exactly into the string. Therefore, they accumulate. Everything else is basically noise. Okay, now that we talked about strings, there's of course the second example of air, right? Air in pipes. The string, you had both ends held together, so both ends are nodes. In pipes, both ends are open. And we'll see what happens here. It's moving too fast. We're able to appreciate this. So let's put this as negative pi here, pi, and let's play this again. So in strings, what we had is the ends of the strings were held together, right? In pipes, the ends of the pipes are open. And so the ends of the pipes have to have antinodes, like this. I'll explain to you why this is in a bit. So we have a pipe, right? In this case, this has to be a sound wave, right? So sound waves are vibrations of the air molecules, right? And we saw this in longitudinal waves. So wherever the sound is compressed, over here, for instance. This is a compression zone. The other places will be a refraction zone. And the first question would be, why does this even bounce, right, off the ends of this pipe? So let's look at what happens. We have an area with high pressure, right? So this is going to be our high pressure area. High pressure area. The parts in between are low pressure areas, right? And these are waves, so they're going to move. They're going to move out. The first wave moves out is high pressure, so it pushes the air around the outside, right? So the moment it goes to the end of this, it pushes out the air, right? It blows out. It was contained by the pipe, but as soon as it's opened, it expands, right? Now let's keep this moving. Next, after the high pressure area leaves, this will all expand outwards. But what happens is you have a low pressure area here. Low pressure area. So the air around it is not low pressure, right? It's normal pressure. It's going to rush into here. Go in as it leaves. And it's going to create a second wave going backwards, the opposite direction. Right? So this is what causes the reflection in the open end, first of all. Yeah, not all the energy is reflected theoretically, because some of it left in the end, but enough of it is reflected so that it bounces around again and again in the inside, right? And it will cause a standing wave. The thing about the standing wave is that any particle that is sitting in this edge is able to move maximally. There's nothing stopping from moving, right? So it cannot be a node. It has to be an antinode. Any particle here, like we said, moves left and right at the maximum amplitude because nothing is able to stop it. All right. Next, what's going to happen is there's going to be, I'm going to write this as displacements. Like that. This is antinode, so any particle here can get maximum displacement, right? Like so. Any particle here in the node doesn't move, right? And it's gonna keep going. And one question here is, you'll notice that in all these pictures, there's one solid line and the second line is dotted, right? And the reason for this is because what you're actually seeing is this. You don't see both ends at the same time, or you just see one end. So this is the solid line. The dotted line is that half a period later, that's what it will be, right? So at any one time, you can only see one side of this. The dotted line is what you would see after half a period when it goes to the other side. So this happens at the nodes, they don't move. At the ends, they move maximum amplitude. Any point between isn't either maximum or minimum, right? They just move up and down, but less than the maximum. If you look at this, we learned how to find the compression and refraction zones, right? So this is the first harmonic. If you look at the first, second, third harmonics, this is still half a wavelength, right? So the equations are all the same as the closed ends. This is still one full wavelength, so for the second harmonic as well, the equations are all the same. So we're not going to prove this again, just know that for closed end or open ends, the equations are exactly the same. What I'm going to do with these pictures now is I'm going to erase one side of them, and I'm going to show you what the compression and refraction zones will be, right? So let's use the second harmonic for this example. In the second harmonic, I'll use a whiteout, and I'm going to make this line a dotted line. That's just too thick. Okay, good enough. So we only follow the solid line. Okay, sound good? We do the same thing we did. We're trying to find refraction and compression zones, which is we're going to highlight the different areas, right? And we're going to say everywhere that's highlighted blue has displacement to the left, right? Everywhere there's highlighted blue, everywhere that is highlighted yellow has displaced towards the right. At this point here, the molecules are moving away from it, so this is a refraction or compression zone point. Refraction. Refraction point. On the other hand, this point here in red, all the molecules are moving towards it, so it's going to be compression point. Right? Now let's do this again when after half a period when this line goes the opposite side, right? So I'm going to copy this. Going to paste it here. Now it's the second harmonic, and I'm going to dot the bottom line. So this. Okay, that's good enough. So now we will follow this line, right? Which should be the opposite. Yeah, it's the opposite. Now we're gonna make this. All the molecules here are displaced to what side? Negative, right? Negative is left. So all these molecules are moved to the left. Again, in the yellow zones, everything is positive. Displaced is positive, so everything is displaced to the right. Therefore, the new refraction zone is going to be here. And the new compression zone, sorry, this should be to the right. So to the right. Now this is a compression zone. Right? So they alternate. This is the node, right? So it compresses and expands, compresses and expands. This point itself doesn't really move, but everything moves around it. Right? This is the important part, to notice that it's not the antinodes that have the compression and refraction points. It's the nodes that alternate between that, right? So everything around it moves towards it. One cycle, the next cycle, it moves away, towards, away, right?